Here we go, second last video for 8201. We're going to take basic integration just using that general power rule, which was so nice, and we're going to realize that sometimes it doesn't work, and we're going to have to use integration by substitution. Here we're looking at two indefinite integral questions. They're almost identical, except for the one on the right has a power in it. Now the one on the left, we've already kind of covered how to do this. Simplify by expanding and then integrate. So we would start by, I could dump out the two. Apparently I haven't this time, so I'm going to just continue like this. And then I integrate each section separately by using my general power formula. U to the n is u to the n plus 1, over n plus 1 plus c. So when I know that I have a 2 that can stay there. If n is 3, n plus 1 is 4. I have a 16 that can stay there. On the x there must be a 1. N plus 1 is 2. I clean it up. And we're done. Why can't I do this here? Because of order of operations. Before I would be allowed to distribute the 2x, I would owe it to myself to expand that binomial to the power of 11. That's not feasible. That's not doable. That's not time effective. So I need another move that's going to let me deal with these composite functions, these nested functions. What integration by substitution is going to do for us is deal with situations where we needed the chain rule to differentiate. So let's think about what the chain rule was. We had, if you wanted to find the derivative of y with respect to x, and you had like multiple nested composite functions, you could take an intermediate step where you would find dy with respect to u, then find du with respect to x. That's one way of writing it. This is another way of writing it, where you would find, if you wanted the derivative of f of g of x, it would be f prime of g of x times g prime of x, which most simply we usually write as this, v prime of u times u prime. Okay, so what I'm telling you is that if you can create any of these situations where you get yourself into a point where you see u to the n du, then you know that you integrate u to the n to u to the n plus 1 over n plus 1 plus c. This is just logical. If cos u du is your derivative, your integration would be sine u plus c, because when you take the derivative of sine u, you get to cos u, right? So opposite actions. And likewise, if you have sine u du and you want to integrate it, you can bump that up to cos u plus c. But you remember that the derivative of cos u is negative sine, or sine u, negative sine u. Wow. So therefore, if I have a positive, I just have to tack on a negative. This video is just going to look at the first one. The next video will deal with situations 2 and 3, the trig ones. So here's the method. And feel free to pause this video at any time, rewind, kind of just really stare at to see what we are doing. I want to be able to change this. I see a composite function in here. I see this, and then I see it multiplied by something else. So in my mind, if I can make this kind of substitute into the thing, so I make this kind of situation, then that is very easy for me to integrate. And then I can change my u's back to x's like we were doing for the chain rule with differentiation. So recognize your composite function. Here it is. Inner function, x squared plus x. Outer function, that to the power of 11. And then we write it first. So all I've done is rearranged. So I have 2x onto dx afterwards. So how can I get this to look like u to the n times du? Well, let's define some variables. Let's make u equal to the inner function, just like we would normally. when we were doing the other way, when we were doing chain rule. So u is x squared plus 8. Now, if u is x squared plus 8 du, and now I'm going to write it as du over dx, that intermediate step, just because I want to be able to do some rearranging. And then I will take the derivative of x squared plus 8, which is simply 2x. I want to isolate du. So I'm going to rearrange this to du equals 2x dx. Now I want to be able to substitute du into this equation for something, and suddenly I can. So I can rewrite this integration in terms of x as an integration in terms of u. And here's what it looks like. The integral of, I don't know why I put it in brackets, u, because I'm changing x squared plus 8 to u, to the power of 11 with respect to x, u, sorry. And then I do it, which means I'm going to get to u12 over 12 plus c. My last step will be change u back into x squared plus 8. And my answer will be x squared plus 8 to the power of 12 over 12 plus c. What's my check? Your check is always by differentiating. So if I took what I see here, my answer that I've boxed, I will get 12, and I differentiate it. 12x squared plus 8, using the chain rule, times the derivative of what's in the brackets. There we go. And if I were to clean it up, I get 2x onto x squared plus 8, which is exactly what I had. Oh, sorry, to the power of 11. Drop the 11, wah wah, which is exactly what I had there. It's weird, but it works, and we give you questions where it's going to work. I'm going to go through about 3 or 4 examples just so we really get a hang of it. So when I look at this, first thing I see is where's a composite function? There's like a quotient thing going on. I'm definitely going to change the denominator into something that is less gross. Let's do 4x squared plus 5x plus 1 to the power of negative 1 over 3, reflecting both the radical and the negative, the fact that it's in the denominator. And then I'm just going to write the 8x plus 5 after it. And that's my goal. I want to make this u, I want to try and get this equal to du. Sometimes it happens right away, sometimes it doesn't. So if u is 4x squared plus 5x plus 1, du dx is going to be 8x plus 5. That looks awesome. If I rearrange this, suddenly I have du is 8x plus 5 dx, and I can substitute both u and du into this integration, and suddenly it's going to look like u to the power of negative 1, 3 over 3 times du. And that I can integrate using the u to the n plus 1 over n plus 1. Here we go. N plus 1 is 2 over 3. And we could say that's divided by 2 over 3, or get our big kid pants on and say it's times 3 over 2 plus c. Coming back up, let's rewrite that. 3, replace u with 4x squared plus 5x plus 1. Always go back to x to the power of 2/3 over 2. And certainly plus c. You could rewrite that as a cube root of something squared if you wanted. Either way works for me. One that looks quite easy but maybe is a little bit different. Let's rewrite it so everything is in the right order. Put the composite function first. The nested function, I see a polynomial to a ridiculous power. I see something that I hope turns out to be the derivative of what's in the first brackets, dx. So once again, we set u equal to what I see in the brackets, x squared plus 3x minus 4, which means du dx, just set it up this way, even though I usually just say du, I want you to do the du dx so that you can rearrange, equals 2x plus 3, which means du is 2x plus 3 onto dx. Okay, this is not awesome. That's not what I have in this part. But if I were to take this and factor out 2, I'd have this situation going on. And that's okay. I can absolutely substitute this piece in for this piece. So when I rewrite that in terms of u, switch colors here, I'm going to have the integral of u to the power of 5, and I had a 2 times 2 du. Boot the 2 out, and here's what we're doing. Use your general power rule. Just going to multiply u to the 6 over 6 plus c equals u to the 6 over 3 plus c. And then final answer, let's replace u with our original polynomial. We get x squared plus 3x minus 4 to the power of 6 over 3 plus c. If you're unsure if you've done it correctly, differentiate. You should get back to this bad Larry here. So maybe we're getting more confident now. We look at this one, we're like, okay, you told me to rearrange it, I'll do that. But I don't like it. And I'm going to go the long way. Normally I would immediately kick out the 5. But I'm not going to right now. So u is going to be within the brackets, x4 minus 27, which means du with respect to x is 4x cubed. That's not what I have there. And in fact, du is 4x cubed dx, which is not what I want to sub in. So what if I brought the 4 over to the left side and just did this? d over 4 equals x cubed dx. Now I have something that will substitute in. It'll substitute in just for that part, but that's okay. The 5 that was already there is a number. I can kick it out or just ignore it while I integrate. And the 4 that I put below the du is also just a number. Totally allowed. So here's what I'm proposing. Now we're going to do, and maybe I'll leave the 5 there for the first step, u cubed times 5 times du over 4, and that's it. That's what we've got. We did our substitution. Now let's boot out the 5 over 4 and just deal with u cubed du. We're allowed to do that. So we're going to have 5 over 4 multiplied by u to the 4 over 4 plus c, which means we'll have 5 over 16, and then let's change it right now onto x to the power of 4 minus 27, also to the power of 4. Oop, and that's very terribly written, but you know what I mean. Cool. Continuing on, remembering we're flipping and flopping, we're just trying to make that substitution, something where we can replace a string with du and u. Okay, right away I'm just going to rewrite this as 4x plus 3 to the negative 1/2 dx. That's what I've got. Let's make u 4x plus 3, which means du dx is 4. And lots of steps right now just to try and keep it clear. If I rearrange, I get du equals 4 dx. I don't have 4 dx, I have just dx. But if I move the 4 over to the left side again, like I did last time, I can have d over 4 is equal to dx. And I can sub just like this. Here we go. So suddenly my integral becomes u to the power of negative 1/2 times du over 4. You can kick out the quarter if you want. If that makes it easy for you, you can leave it and just ignore it. Bring it back after. Whatever works best. So if we do the integration of u with respect to u, we're going to get u to the power of 1/2 divided by 1/2 plus c. And I accidentally changed. I got excited and went ahead in my head there. So let's leave that as a 4. I don't get to move that yet. If you divide by something by 1/2, you multiply it by 2. So baby steps here. 2u to the 1/2 over 4 plus c. And now all at once, reduce a fraction to 1 over 2. So I know my answer is going to be over 2. Change it back into 4x plus 3. Change u back into 4x plus 3 to the power 1/2 plus c. This is correct if you also wanted to write root 4x plus 3 over 2 plus c. Totally fine as well. Either or. When we're talking about definite integrals, we can totally do the same thing, method of substitution. It's neat because we have two options. We could find the antiderivative of a and b relative to x, or we have another option where we find the antiderivative of a and b relative to u. And these will give you the same answer. It's just kind of neat to compare. You choose the way you like best. All right, so let's look at this bad Larry. Nothing is different in the process to start. And in fact, if we do it relative to x, we're going to go all the way to the end, find the antiderivative, and then use the upper and lower bounds, x equals 2 and x equals 1. So here we go. We're going to pull out the 1/3. And I'm going to write the composite function down. Put the x afterwards just to see how I can make it all work out. I make u 4x squared minus 11, which means du with respect to x is 8x. Okay, rearranging to try and get this kind of situation, so I can substitute that for du because I know this part will be u to the 4. Okay, we're going to end up by doing the same thing we've done every other time. Oops, du over 8 is equal to x dx. So that's what I can sub in to replace this. My goodness, what a mess. Okay, so we have the 1/3 on the front. We've got an integral sign. We now have u to the power of 4 du over 8, which will give me, I'm going to kick the 8 out. 1/3 times 1/8 is 1 over 24. And then I'm going to have u to the 5 over 5. And I'm working towards the antiderivative here. So now I'm going to change everything back. I get 4x squared minus 11 to the power of 5 over 120. And that's my antiderivative, capital F of x. So what do I owe it to myself to do? I need to find the antiderivative at 2. Substitute 2 in for that x. Do your math. I don't need to show you this. And you're going to get 26. Find the antiderivative at your lower bound. Substitute 1 in for x. You're going to end up with negative 7 to the power of 5 divided by 120, which should give you something in the range of negative 140. Your answer is going to be f of 2 minus f of 1, big F, antiderivative, and you're going to get 166 as the answer for that definite integral. Now let's look at the other way. We're going to do the same kind of stuff. We're going to end up with u is equal to 4x squared minus 11. But I want to change my boundaries now to be relative to u instead of relative to x, because these are really like x is 1 up to x is 2. And I want to have it be u. So all I have to do is sub it in. If I want those boundaries, do this math. It'll be 4 times 1 squared minus 11. And up here, it'll be 4 times 2 squared minus 11. And suddenly, my integral with respect to u, not x, now maybe I'll put u equals, u is going from -7, that's a math here, up to 4 to 16 minus 11 is 5. And I'm going to steal some stuff from what we did before. We kind of were at this point. This is no different than what we were doing the previous thing. U to the 4 du. When you do this math, you get your f of u, let's say, instead of f of x, and you have that u to the 5 over 120. And now, instead of subbing in 2 and 1, which were x's, you can just go directly to subbing in 5 and -7. So your upper bound is when u is equal to 5. And you're going to have 5 to the power of 5, divided by 120, which is, surprise, surprise, going to give you 26. And when you find f of when u is, the antiderivative when u is -7, surprise, surprise, you're going to get -140. And then you subtract 26 minus -140, and you get the same answer. So either way works. Kind of cool. So when you see these integrals where you can't just separate a fraction or expand simply into term-by-term integration, you're going to look for the composite function and the inner function that is to a power. The inner function is the polynomial or what have you. Make that u. Reorder it if you want to, so the composite is first and you can see what you're trying to find for the derivative dx. So now you're going to set u equal to that function, that inner function, and then you're going to find the derivative du dx. And you rearrange that du dx formula until you get a clear substitution that works for du. Integrate using the power rule, because you're going to be u to the power of whatever. I guess I should put u to the n du using the power rule. And then once you've got that, you switch u back to a function of x, clean it up if you have to, and check your answer by differentiating it. You should get back to the original question. It's weird. It works. Have fun.